talk is about jet quenching and jet transport coefficients. And I was told not everybody here is in heavy ion physics. So maybe just a few slides of introduction. Now this is stuck. Come on, okay. Every software is different. So this is an overview of the talk. It's not the order in which the talk is going to go. It's sort of the topics that I will be covering. So, some introduction to scale dependence and asymptotic freedom, which probably everybody here knows about. But I just say that to sort of start the story, and then we will get into different jet transport coefficients, but focus our attention on what is the leading jet transport coefficient, which is often called Q hat. Results that you will see will come from two of the major theory and theory/experimental collaborations that I've been part of, which is JET and JETSCAPE. JET is, of course, was an all-theory collaboration, but JETSCAPE is a theory, experiment, computer science, and statistics collaboration. And we'll spend a lot of time talking about scale dependence, how things change with energy scale, virtuality scale. It changes how the jets evolve, how things change with scale for jet evolution, how things change with scale for the transport coefficient itself. A few extra topics which we could cover is these data-driven extractions, which is becoming a big rage nowadays. Which is basically another way of talking about Bayesian analysis and lattice calculations of Q hat that I've been part of. But if you want to sort of follow the talk, I have these snippets on the side. Right, these are basically, you can't read anything on this. It's so small. Hopefully you cannot read. I cannot read anything. This is these are sort of thumbnails of plots that you will see throughout the talk. And as you notice, it starts blank and then detail starts to get filled in. And when it gets completely filled, you will know you are about 3/4 of the talk in. Okay. That's sort of how you keep pace with the, where you are in the talk. If I had to give you the basic idea of the talk in 20 seconds, or maybe 30 seconds, I would say that the salient points are that to compare, theory with a large amount of data eventually requires a certain amount of modeling. It's unavoidable. And I'll try to argue to you that a simulator or an event generator is essential for this comparison. And you need a framework to separate theory, pure theory input from modeling. And whenever you have a large amount of data and extensive theoretical framework, they are going to be parameters, some of which are actual information that you want to extract, and some of these are just parameters that came in because some part of the physics was not completely clear and you needed to settle that. But having multiple parameters basically means that some kind of Bayesian analysis will happen, has to happen. And only some of these quantities can be calculated from first principles. Okay, and some of these will remain as model uncertainties. Okay, so at some point, somebody should stop me if I'm saying too many simple things and wasting time, because then I could go talk more about the more interesting stuff. So just a brief introductory slide on Unearned Qcd. As most of you know, It's a theory of quarks and gluons, involves color. But the kind of more important point I want to focus on is this plot here, which is that the coupling, because of the non-abelian nature of QCD, tends to weaken, and weaken very quickly as one increases the scale of the interaction. Okay. And this is a theme that will sort of show up several times in this talk. Another, if you're not from heavy ion collisions, one of the most more canonical examples of QCD is to look at deep inelastic scattering. And an interesting aspect of deep inelastic scattering is the scale dependence of structure functions. And what that kind of means is that if you were trying to hit a proton with an electron, as one does in deep inelastic scattering, if the interaction was at low energy or low scale, then basically what that means is the electron kind of scatters from the proton kind of from very far away. And it basically sees a small colorless object, right? And as you increase the energy or increase the scale, it starts to go closer to the proton and it begins to see substructure. And as you keep increasing the energy and the scale, you get even closer and closer. And at some point you begin to notice that there is more than just 3 quarks in a proton. You have lots of gluons as well. Okay, and at this point, we can start describing the structure of the proton in terms of structure functions or parton distribution functions, which is basically, you know, the number of these partons in bins of momentum fraction. That's sort of plotted over here. This is from HERA data. And as you keep increasing the energy scale, qualitatively, the picture remains more or less the same. You get closer, you see more things inside the proton. You know, and the structure functions are changing. You know, you have lots of glue in the proton, for example. Right. So this is one way of understanding a strongly interacting object at very, very high resolution. So another aspect of this asymptotic freedom is obviously the weakening of the force as you go to high momentum means that if you were now going to a medium, you'd have a weakening of the force also at high temperature. This is the standard story of heavy ion collisions. If you're at low temperature, you have a nucleus, but when you heat it up, at some point you will start having excitations of mesons and baryons, which we now believe is roughly in the region from 50 to 150 MeV. And at some high temperature, you may have a plasma of quasi-particle quarks and gluons. My sense is that, and this is a personal opinion, that we still haven't hit the quasi-particle regime of the Quark Gluon Plasma. You know, color is deconfined, but probably the excitations are not quasi-particles, maybe to be seen. And the way you heat matter, again, if you're not from heavy ion collisions, which is basically by colliding heavy ions. And I just want a simple a movie that everybody likes to show. You know, you collide the ions, you make this heated material, which very quickly turns into hadrons, which then go to your detector. And I don't think we need to see the whole movie. But just to use that as a segue into explaining some of the plots. So a lot of the plots that you will see will be in centrality, which basically is a quantity that expresses how head-on the collisions were. Right. So, and it's kind of a reverse scale where low numbers kind of mean that you're basically almost head-on collision, and high numbers means you're almost peripheral collisions, you barely touched. And if you look at it sideways, then of course, the hadrons that are coming out will be classified in terms of their transverse momentum and either their rapidity or pseudo rapidity. And these should be familiar with anybody from particle physics as well. And here's a sort of plot from Alice for different centralities, where you look at, you know, sort of the bulk behavior, where most of the hadrons are sort of coming out of these collisions, and they're organized for the most central out at the top, and and less central at the bottom, and they're kind of artificially separated by these extra factors, but it is true that the central has more particles and less, and it gets less and less as you go to more peripheral collisions. Okay, as most of you know, that you have a low viscosity matter, that is low specific viscosity matter that is being produced at RIC. Excuse me for a second. And the way we know that is by looking at not the most central collisions, but looking at sort of semi-central collisions where, you know, you look at particle production. I'm kind of rushing through this because I'm assuming everybody knows this story. And if you want me to slow down, somebody should say something. So you take the yield of particles in the azimuthal direction, and you can decompose it in terms of Fourier harmonics, and that tells you how the momentum, final output of momentum, the final momentum of the particles, you know, is reacting to the geometry of the initial state that was being produced, and that basically tells us that the particles react very well, which means that the system had to have very low viscosity, which means it had to have a very large cross section, and so it has to be strongly interacting. And so some results here from the JETSCAPE collaboration for bulk and shear viscosity, and I could get you to focus up here on the shear viscosity. You find that it is literally quite low, very close to the bound set from ADS-CFT. Is another plot from Charnay, Kapustin, and McLaren. You know what one expected sort of theoretically by extrapolating known theories from some years ago, and the experiment. These are obtained. I don't know if I can back up from here. Right, these plots are actually obtained by fitting with data. So you have a full model with an initial state and a hydrodynamic evolution, and final hadronization, and you fit to data, and then you try to extract what the viscosities were, and that's what the extractions look like using a Bayesian analysis. Okay, and again, if you notice up here, this is the log. This is from JETSCAPE as well, and you see a lot of JETSCAPE results because they're very easily accessible to me. Okay, so the matter is strongly interacting. So it may or may not be the weakly interacting plasma of quarks and gluons or quasi-particle like quarks and gluons. So how do you study substructure? Well, this is why I showed you the example with the proton. The proton is of course strongly interacting, but we can study its substructure. And the way we do that is by using a high resolution or a short distance probe. And the same can be done for the Quark Gluon Plasma. And the tool for that is basically JETS. Okay. But of course, there are many caveats to this. So, and if I could combine all of them into one caveat, and that would be that JETS are really complicated. They were initially supposed to be kind of simple, but they turned out to be more and more complicated with time. JETS, excuse me for a second. So JETS start out in a hard collision. They tend to be very virtual objects, and as when they start out, they are very small in transverse size. They live for a short. The original parton probably lives for a very short time, but then it decays into partons that live a little bit longer. They are a little bit closer to on shell, and so their transverse sizes are increasing. And as the time goes on, they live longer and longer as they get larger and larger and larger. Okay. Now, this is of course very well understood process in the vacuum, but we have to basically put it inside a moving, evolving medium where every stage of these jets will interact with the plasma and it'll change. And change means there's been energy momentum exchange with the medium. Okay, and this energy momentum exchange will basically show up in excitations of the medium, which we often call medium response. Okay, and some of that will show up at momentum scales of the bulk medium, and some of the jet will cleanly get out of the medium and hadronize and be clustered as a jet in your experiment. But some of that, what you catch and think of as a jet, will be an excitation of the medium as well. So all of that gets mixed up together in the experimental observation of a jet. And we have to basically tease all that apart to the extent possible using various jet observables. Okay, so everything other than leading hadrons includes, leading hadrons means looking at sort of the highest PT hadrons that came out, where you can be more or less certain that these things probably hadronized outside the plasma. That the parton came out cleanly and then hadronized outside, and most of the hadronization was not affected by the plasma that's coming up behind it. If you now talk about how those partons in the shower were affected by the medium, changing the jet basically meant changing the partons, changing how many were emitted and how their momentum changed. This is based on interactions with the medium, and so basically it's momentum exchanges with stuff in the medium, and the way we classify them basically is in very simple ways, and we'll come back to this again and again, is that you could have exchanges which change the transverse motion or momentum of a parton that's propagating. The coefficient that does that is called Q hat, and that basically quantifies the amount of transverse momentum squared obtained per unit length. There could be longitudinal momentum exchanges, which could lead to a drag, could also lead to a diffusion, and that's often called E hat, or the elastic loss rate. And these basically describe how the medium would change one parton, right? And then you have to have this happen over all the partons in that shower. Let's focus on Q hat for a second, because after a lot of, we can say now with a good deal of certainty that Q hat is probably the most dominant transport coefficient that controls most of, or a large part of the quenching that we see. People often started out thinking about it as an intrinsic property of the medium, and it scales as energy cubed or temperature cubed. The dimensionality is PT. It's remember it's transverse momentum squared per length, so its dimension is like temperature cubed. And it should have some transition between a confined and deconfined phase. And if you want to calculate with it, you have to scale it with some intrinsic quantity in a realistic simulation. If you really want to put it in a simulation, so the way this works is you put it in a simulation, you run the simulation, you compare the experiment, then you extract what that Q hat was. Oops, what happened? So how do you get it? Even before any of the experiment starts, you can start trying to calculate it in hard thermal loop perturbation theory. And some example of that is on the slide. And if you did calculate that, this is what it would roughly look like. It would go as, there are two couplings, so it's alpha squared. It's dimensionally temperature cubed. That's what you expected. And because of this in the one exchange approximation, if you integrate over this, you'll get a logarithm where the lower scale is given by the Debye mass. That's sort of the minimum momentum that this exchange gluon can have. And the upper limit is sort of given by the maximum exchange you could have with a propagating jet. And here E is the energy of the hard parton, which is in yellow. So if you take that you put E as 100 and you let the scale in the alpha S sort of range, vary between these two ranges, this is what you would get. You get these bands. So the gray band is just for your information. That is for a quenched plasma. That is it's for a plasma with no quarks, only gluons, so flavor 0. And the other one is for a 3-flavor plasma. So that's kind of our initial expectation before you do any kind of experimental study.
Abhijit?
Yes.
A quick question about this. When you say NF equal to 3, quick question about this graph. When you say NF equal to 3, is that for 3 massless quarks?
Yes. Yes.
Thank you.
No mass. No mass in this. Right. Yes. So it is in the, it's almost a textbook version of the hard thermal loop perturbation theory, where we're assuming 3 massless flavors of quarks. Yes. Yeah. Thank you. That's a good question. One thing I draw your attention to, that if you look at these temperatures, if you look at these scales that go into this in this plot, and if you put in a canonical temperature that we think exists at least like 250 MeV, 2 pi T is like 1.5 GeV. Okay, so if you go back to this plot now and try to figure out where is 1.5 GeV, that's like over here, where the line kind of ends. So is perturbation theory okay at these scales? Hard to say. So the way the object that we will keep comparing with in the experiment often will have the form of a ratio, which we call nuclear modification factor. Not everything is going to be a ratio, but you'll see a lot of these ratios, which we call RAA. And the way we think about that is, if you think of a collision of 2 heavy ion collisions where jets are being produced, and these jets now have to go through the medium, and you capture them, then the RAA is sort of the yield of jets, of hadrons, whatever you are interested in some range of centrality or impact parameter, divided by the same yield in a PP collision scaled by the number of expected nucleon-nucleon collisions that could happen in a heavy ion collision. Okay, and so if you try to calculate that, the numerator, that is, there'll be some integration over impact parameter. It has to have some integration of a transverse location of where the jet would be formed. Okay, you would integrate over the probability of getting a parton from one of the nucleons in say the B nucleus, and the probability of getting a parton from the A nucleus coming, and there'll be some cross section which will tell you how these two collide and produce 2 back-to-back outgoing hard partons. And then there will be a quantity that calculates how these things lose energy in the medium. So that's what the delta E, probability of delta E is, like probability of losing energy. And then there'll be something that tells you how this fragments into hadrons or into jets or whatever you have. And it's of all of these, most of this part is sort of standard PQCD objects that you could calculate also for the case of PP collisions. The only extra term is this P of losing energy, and that is the thing that is directly proportional to the value of Q hat. So that's where Q hat basically enters here. Since this is a ratio, when you plot it out as a function of PT, I forgot to tell you that Q hat, of course, depends upon where you are in the medium, right? Where the interaction happens, and the interaction happens continuously. So it'll depend on things like temperature cubed or entropy density. And you'll see an example of that in just one slide. So again, this is a ratio, which means that if nothing happened in the medium, then when you plot it out, you expect the number to be at 1, irrespective of how it's binned. But most of the plots that you will see will have things that are less than 1, which means that there was some kind of suppression or quenching of this ratio. out of this quantity, right? So, you'll see plots which have 1, and then you'll see the line sort of below 1. So here,
Abhijit, can I ask
yes.
one question, quick question over the previous slide?
This one?
Yes, this one. So you said all the things before DP3 are standard PP, but there is one thing that you said that initially you create a virtual parton, and usually when we just do a PP calculation, you say that you create an on-shell, 2 on-shell back-to-back partons, right? Here, how does the information of the virtuality go into these quantities, sigma, etc.?
So this all falls under sort of factorization.
Yeah.
Okay, so the idea is that at the scale at which one calculates the 2-to-2 cross section, any virtuality of both the incoming or the outgoing partons is negligible compared to the scale at which they hit each other. Okay, and so the incoming guys are space-like virtual, the outgoing guys are time-like virtual, but that virtuality scale is considered much, much smaller than the scale of the interaction. So the fragmentation function has a scale, right? And it changes with the scale, and that scale is basically the virtuality of the outgoing parton, right? So, but we just, again, it's always in this limit of factorization where you're assuming that there is a large difference in the scale between one interaction, which produces the jets, and the interaction of their subsequent evolution.
Okay, thanks.
Happen. Okay.
Yeah.
Right. So here are some examples. It's from this very famous paper. I just cannot. I just keep laughing when I say that. So I'm also an author on the paper. So it's like beating your own drum. This is a paper where many different. This is from 2014, and at that time, there was a lot of debate on what is the right formalism for doing energy loss of partons in a medium. But regardless of that debate, so we just said, let's put that aside for a second, okay? And let's compare on the same medium. Let's make sure the hydro simulation is, let's assume there's only one hydro simulation everybody has to agree on. And then people just make their jets go through that same hydro simulation. So I don't know if you can read any of these are from the Columbia group, CU jet. These are my calculations. These are from, oh dear, who are these? I want to say this is the McGill group with Martini, could be wrong. And this is another group. And what we are doing is we are comparing with the most central collision at RIC. That's the top. So the data points are all the same, by the way, even though they don't look like it. The data points in the top plots are the same. The data points in the bottom plots are the same. So these are from CMS. So these are our LHC data, and these are RIC data. Okay. And so we basically compared them, and as you can see, the predictions are not the same. They're all a little bit different. That's because the underlying models are different. But what is same in all of them is that all of these, this is a plot of Q hat scaled by temperature cube as a function of temperature, had to rescale the Q hat. The normalization at RIC was higher than it was at the LHC. Okay. And it's true for, and you see all these different bands in here are for different models, and all of them had to rescale down for the LHC. Some of them use HTL, and you can see that, right? You can see that upward going curve. That's from those HTL lines that I showed you before. So let me take those points and put them on our plot. Okay, so there they are. So one for RIC 158C. And again, that's just in what I just said. To be clear, the difference between the maximum temperature at the LHC, based on that hydro simulation on which people fitted, the maximum temperature at LHC was only 20% higher than the maximum temperature at RIC. The momentum of the jets that people were looking at the LHC, and so let me back up a second and say that what you saw there was leading hadrons, not completely jets yet, just leading hadrons, but the momentum that went in at the LHC were 5 times larger than they were at RIC. Okay, but never mind all that. When people saw this, the first notion, the first thought was, if I had plotted Q hat over temperature cubed, this is what it might look like, right? That there's some kind of bump at the transition temperature. I have to admit that at some point, even I began to believe this, but I don't believe it anymore, and I'll tell you why. If there was a bump, it would have showed up in many, many other observables, and it didn't. Now, since then, there's been a huge change in the paradigm of how we think of jets. Remember all those different energy loss models that I showed you at that time? Over time, what has happened is they've all now sort of been bunched into different classes of models, okay? And they depend, and we've understood now that some of them are applicable in some part of the life of the jet, and some are applicable in some other part of the life of the jet, okay? And they should really be used in this kind of multi-stage formalism, right? And this is sort of what the picture looks like, that, you know, how if any of us think that, you know, there's a hydro simulation, which is this gray blob down here, right? Just imagine time is going from the left to the right. There's a hard interaction that produces a hard parton, and initially it almost behaves, its scale is, as Rishi pointed out, you know, the scale is smaller, much smaller than the scale of the hard interaction, but this still, its virtuality is much larger than any scale in the medium. And so in the first part, it almost behaves as if it's in vacuum and has very, very rare scattering. So, you know, I call this sort of the radiation dominated regime, where there are lots of radiations and occasional scattering only. And at some point, the virtuality comes down to the scale, 2 times the energy times Q hat, and it transitions to a very different kind of regime where, you know, the radiations become rarer, but the scattering becomes much more prevalent. Right? This is what I call the scattering dominated regime, where there are many, many, many scatterings per emission.
Abhijit, just to clarify, did you mean Q square? Okay, no, sorry, it's fine. Sorry, I got it.
Go ahead. What was the question?
I was thinking something wrong. Now it's clear to me.
Okay, so yeah, so by Q squared, I mean, so when I just say Q squared, it means what is the virtuality of the parton, which of course is changing as it emits, you know, partons and goes along. Except when it comes down here, you know, when it comes down here, there's so much scattering from the medium that just maintains the virtuality. Okay, or maintain is probably not the best word. It kind of slows down the rate at which it falls. Okay, so how did I get that estimate? Well, if you say that the generated virtuality is completely driven by scattering, then given the lifetime of a parton between splits, the generated virtuality would simply be Q hat times that length. Remember, Q hat is transverse momentum squared per unit length. Length and time are the same thing. Basically, thing is moving at the speed of light. We're not doing heavy quarks like Rishi right now. So it's Q hat tau is the medium generated off-shellness, and tau itself is the lifetime of a parton, which is by uncertainty relation, you can argue is like twice the energy over the actual virtuality of the parton. And then all you have to do is say that, well, let's set Q squared equal to Q medium squared, and then just work through this and you'll get this relationship. Okay, so when Q squared drops down to this, you transition. So over here, the physics is DGLAP-like. the simulator that does that is called matter. As it comes down here, the physics is BDMPS like. So this is Dokshitzov-Gribov, Lipatov, Altrelli, Parisi, Bayer, Dokshitzov, Mueller, Penny, and Schiff. I always like to point out the D in both is the same person, Yuri Dokshitzov. So this is BDMPS. We call this BDMPS like stage where there are lots and lots of scattering and rare emissions. Simulators that simulate this are, there's one called Martini, which is developed by the McGill group, and there's LBT, which is developed by the Berkeley group. And also you can ask, I have to ask you, Rishi, how long am I supposed to keep talking? Maybe I should just go to ask that.
Yeah. So it's 1 hour, so till 6 o'clock here. So right now you have about 20 minutes.
Okay, that's a lot of time. Okay.
Yeah.
All right. I think it's fine. The other question is you might ask, so that was the virtuality where we have the transition from what is the typical time that a parton would spend in one zone versus the other zone? And you want to ask that question because you want to know, is there a reason for you to simulate both of these separately? Because for a long time, people said, well, the initial zone is for a very short time. And so if you ignore it, the error is negligible. And so you can estimate that by the same formulas that I just put down, that the time is 2 times the energy over the virtuality squared. And so if you ask what is the virtuality squared at a given time, it's about 2 times the energy. Just flip this around. At any given time, the virtuality of a parton would be roughly given by this expression. And then you just equate it. You just equate the Q squared to be Q medium squared and work through it. And you find that the time at which the transition would take place would be square root of the energy over Q hat. And that's interesting because that would tell you that the more energetic the parton is, the longer it will be in this deglap phase, the later it will transition. The smaller the value of Q hat is, the longer you will be in this deglap-like phase. Okay. And that means that different parts of the jet transition from this high virtuality state to the lower virtuality state at different times, right? You should think of each of these emissions as like a mini jet coming off the jet itself, and then they themselves will have splits and all that, and you can calculate their virtualities as well. And basically what will happen is that a lot of the soft stuff will go into this multiple scattering stage, but the core of the jet will sort of remain in this high virtuality state for quite some time. And I and my collaborators had to estimate what that would look like. So if you took vacuum-like splittings only and tried to estimate and just shut off any interaction with the medium that you could have, that's sort of shown here. I just want to focus your eyes on the dotted line and the dashed line. Okay, so the dashed line, so down here, so this is the amount of time spent in the deglap phase, and the dotted line is the amount of time in the BDMPS phase. And if you look at these two lines for a while, you can convince yourself that if I take the red and I add the blue, they add up to the same number. Sort of gives you this almost the same amount of time, right? So at lower energies, this is energy of the parton, lower energies, they spend a very small amount of time in the deglap phase and a lot of time in this transport or BDMPS phase. But as you increase the energy, they end up spending comparable amounts of time in both these phases. Okay, so you can see this is the time in Fermi. It's almost to a 200 GeV parton would almost spend half of its time in the deglap phase if you estimated this using vacuum splits. Now, if you use medium induced, some rare scatterings, the rare scattering slow down the rate at which the virtuality drops, and you find that this curve now switches into this, right? So that you spend much more time now in the higher virtuality phase because the scattering basically slows you down. And then you could say, well, maybe the time is not all that important. What is really important is the number of scatterings that you encounter. And so we estimated that as well. And the picture is the same. And I'm not going to go through this in detail, but it's pretty much the same picture that even with the number of scatterings that you encounter, just because you spend so much more time now as you go to higher energy in this phase, a large part of the evolution of the core of the jet is in this high virtuality phase. Okay. All right, so that is sort of the global history of the jet, of the jet's evolution. Now let's talk about how the jet interacts with the medium. Okay, obviously it's a process of multiple scattering, and we make an assumption that all these scatterings are independent. Okay, and there are various arguments for that. And it takes a while for each of these scatterings to take place, and so jet's going at the speed of light. That just means that whatever's happening over here is not going to be able to influence the next parton, the next scattering, and so on. If you take any of these scatterings, this is basically, yes.
This is, I mean, I wonder whether this is the same as the BDM PMS assumptions.
Yes, it is. Yes, this is, so what I'm saying now has got nothing to do with whether you're in the DGLAP phase or the BDM-PS phase. This is generic to all energy loss calculations.
You say that multiple scatterings are not correlated, you don't mean that there's no LPM effect.
No. There is LPM effect.
Okay.
I'm just saying that you know, the object that you hit here is not going to be able to propagate some signal to the next object that you're going to hit.
Okay, great.
The LPM is happening at the jet level. Yes, so the jet is correlating them, but there's nothing other than the jet correlates them.
Thank you.
Okay. So right, so each of these gives you something like a collision kernel, which is like a rate, a differential rate of scattering, and the transport coefficients we talked about, like Q hat and E hat, are basically moments of this collision kernel. And so what you really want to get at is this collision kernel, right? And what you're extracting are things like basically moments of this kernel. And as we move from leading hadrons to full jets, you'll find that you'll become more and more sensitive to the form of this collision kernel. So you can now take that integration over momentum and sort of split it, right? You know, at some scale, and you say, well, below this first part is sort of non-perturbative. It's kind of soft interaction, and there's a part that is a harder interaction. And if it's at a hard interaction, then that can resolve a parton, basically. Okay. And so most of the results that I will show you involve this kind of a hard interaction. There are other models which make this split, and for the soft interaction, they have sort of like a kind of diffuse scattering. And how do you model these? Well, you could model them using HTL perturbation theory again. You could use something like a QGP PDF, or you can use both. You can use a combination, and we will use a combination of this coming up. And what about the parton that goes back out? Well, again, you can use HTL perturbation theory, or you can use what a lot of people do nowadays is basically turn it into a source of energy and momentum, which goes back into the hydrodynamic simulation and generates excitations in the hydrodynamic simulation. So if you had gone with the HTL form, this is what that collision kernel would have looked like. This is from Arnold and Xiao. You can go even further and say, well, what if I now also included the running of the couplings with the integration in the scale? So if you did that, what would happen is once the integration was done, you'd have one coupling at sort of the upper scale and one coupling at the lower scale. And that's sort of what this is showing. Is 1 alpha s at sort of the lower scale of the Debye mass and 1 alpha s at the upper scale. This just comes out of the integration. You need to work it out yourself to see this. And then there's the question of what happens to all the partons that sort of go back into the medium and they start exciting the medium. And I was just telling you that you need to keep track of, either you keep track of the partons, or you have to keep track of the energy momentum that is deposited in the medium. One of the 2 ways of doing the same thing. And how is this done? In JETSCAPE, the way this is done is that every time there's going to be a scattering, you take a blob of the medium where you're going to scatter, you sample a Boltzmann distribution, you take a parton out of it, you scatter. You keep track of the parton that you scattered off, because basically what you've done is you shifted that parton from its energy. And so there's a hole where the parton used to be. And you follow the parton that was scattered, which now becomes sort of part of the jet. And so we call these recoil partons. And they themselves can go on and do further rescattering and generate further holes and further recoils and so on. And you could take, if they're very, very soft, you could put them back in the hydrodynamics, or you could keep them partonic. I'm saying this, I've now said this 3 times, and you're wondering, is there a point to this? Well, we did a very extensive study by not turning them into, just following them as partons, turning them into a source of energy momentum that goes back into the hydro, turning the source that went back into hydro back into hadrons. It turned out that if you're inside sort of the jet core, so that's what those 3 things that I said, right? The green line is if you just kept them in the calculation as partons. The red line, sorry, the blue line is when it just became a source of energy momentum in the hydro, and the red line is if the energy momentum in the hydro was then Cooper fried back into particles. Within the jet cone, it doesn't seem to make too much of a difference. It's just energy momentum conservation. Once you get away from the jet cone, that wake begins to spread away from the jet, and then it depends whether it spreads as particles or it's spreading as part of the hydro. So as you get away from the jet cone, you find that these lines sort of separate from each other, that the weak coupling and the strong coupling response is kind of different. For the rest of the talk, I'm going to be inside the jet cone. So this is still stuff for which I don't have full simulations yet. There are many other ways of doing it. I just need to say that. So, like I said, people who do soft broadening or Fokker-Planck kind of broadening, as in Lido and Tequila, and then there are people who attach ADS-CFT strings to the partons to slow them down, as done in the hybrid model, and so on. And we're not going to talk about this, but I just want to make you aware there are many ways of dealing with this, because this is the modeling part. This is where the theory is kind of not very clear, right? This is the extra modeling that has to go into your simulator. Okay, so the bulk medium we talked about before is very, very well simulated. Also, so we ran simulations, we did Bayesian analysis, we extracted the 8/s. I already told you this before, I'm just telling you this again now, that we now take space-time profiles based on this Bayesian analysis. And we are going to run, I'm going to skip this slide. We're now going to run this energy loss through this hydro. We have a Q hat, which now has this form. You've integrated, and you went to ask, well, what else could it depend upon besides temperature? Right? It could depend on the energy of the parton. It could depend on the virtuality of the parton. Okay, definitely these are numbers which vary a lot between RIC and LHC. It turns out the virtuality also plays a very important role. This was pointed out by a bunch of people. It's called Coherence, which basically says that if the parton is very, very virtual, it's very small, And if it's very small, then the medium has difficult time resolving it. And so at that point, the scattering with the medium should reduce. And we've actually calculated this effect, excuse me, in the higher twist kernel. This is way too much detail, perhaps for this talk. This is basically a formula of the number of gluons emitted in bins of rapidity and momentum away from the jet. Let's say L perp is the transverse momentum of the radiated gluon compared to the jet, and K perp is the momentum that you're exchanging with the medium. What this plot shows you is that the energy loss kernel prefers that the K perp be of the order of L perp. So we set 3 different values of L perp. So if you set L perp to be about 5 GeV, and we ask what kind of K perps are sampled by this, what kind of K perps are preferred by this jet? Well, they peak around 5 GeV. If you set L perp to be 50 GeV, then it wants K perp around 50 GeV. So, it basically wants the medium to make a very highly virtual excitation, which can resolve this dipole and lead to energy loss. And that has an effective reduction in the value of Q hat. The medium has a hard time producing partons that are at a much higher scale than the typical medium scale. And so this really leads to like an effective reduction in Q hat. So there's a multiplicative factor that goes on top of Q hat. There could be other dependencies as well, because you now open up the phase space. I'm going to skip this slide and then go straight now to that. To do all of this, you need a kind of event generator framework. So what is an event generator framework? So event generator is basically a computer simulation that produces experiment-like events, and a framework is something that allows a user to only work on one module while keeping everything else unchanged. That's what we mean by an event generator framework. But you can replace one module and keep everything else unchanged. Now, you leave the hydro the way it is, you leave the fragmentation the way it is, you leave the initial production the way it is, and you just work on the energy loss. Okay. And you could have many different correlated inputs. And many of these, if you increase Q hat, you might have to reduce something else. So all of these are correlated. And every time you change one input, you'll have to compare with a lot of data simultaneously. I'm looking at the clock and I see I'm running out of time. So I'm going to skip these 2 slides on how we do correlations between different parts of Q hat. Let me just skip these 2 slides and let me go back to where we are right now. So this is where we were. We have, the old HDL lines. We have the points from the JET collaboration, and I'm going to show you results for this blue band. This is what we get from the JETSCAPE collaboration. Fits to a whole bunch of JET data, and you see that there's some tension already between. You should ignore the gray. Just follow the green and the blue. There's some tension now between the HTL and what's extracted from the experiment. I just want to throw in another thing, that if you did a lattice calculation of Q hat, the lattice calculation shows up on the other side, right? So it overlaps with the blue band, but it's completely off from the perturbative calculation. So it's interesting where this is going. So what is this blue band based on? Well, it's based on results of this event generator framework that I've been describing all this time. This is from JETSCAPE. If you turn off the medium, it reproduces. There's tons of, I'm going to flash like hundreds of plots at you right now. And you just really have to follow how closely these explain data. So this is the spectrum in PP without any medium. Okay, so it does it pretty good. So you want your event generator, when you turn off the medium, you should go back to PP. You should be able to do that. These are results comparing to leading hadrons, RAA, JET RAA, This is leading hadrons from CMS, the jets from Atlas and CMS, jets from Elise, all at 5 TeV. Central collisions has that form of Q hat I talked about, has a factor that basically suppresses very virtual parton interaction with the medium. As a function of centrality for leading hadrons, for jets, for different centralities, so 40 to 50%, 20 to 30%. This is all, there's no more fitting here. All the fitting was done in the previous slide. As a function of collision energy, we can go down to 2.76 TeV, exact same simulation with no new refitting. You can get leading hadrons, jets, go back down to RIC energies, Phoenix data, leading hadrons, jets from star. These are not exactly jets because they have to trigger on a hadron, but that's because it's an event generator, it functions exactly like an experiment. You can make the exact same experimental cuts on it. Okay. You can look inside the jet, look at the fragmentation function, ratio of fragmentation functions between lead and PP. Okay. You can look at what is called intrajet soft. This is called soft drop, where they cluster and decluster the jet and look at the two largest prongs and plot the distribution of how much momentum fraction is in these prongs. Again, everything here you're seeing is prediction. There's way too much to take in. Right? I'm just trying to show you that the event generator, once set up in this way, just cleanly goes through tons and tons and tons of data. Jet shape, okay, which tells you, if you have angular bins around the jet, how is the PT distributed in these various angular bins? Data calculation. Again, no curve fitting at all. V2, this is probably the weakest part of our event generator, which is that the V2 is a little bit off from the data. This is the V2 for hadrons, this is the V2 and V3 for jets. And that's a little bit less, and this is something that we are working on right now. But as you can see, there was tons and tons of data that we just compared with. And the event generator set up in this way with this multi-stage with a Q hat that has a dependence on temperature, it depends on the energy of the parton, it depends on the virtuality of the parton, seems to be able to give you a good description of the data. Now, none of these plots are Bayesian plots. Okay, so we now have an event generator that seems to be able to explain almost all the data on jets. The Bayesian calibration is going on at this very instant as I speak. We're hoping to have results for quark matter. My sense already is that it'll be very similar to that blue band that you saw. It'll be, maybe the band will shrink a little bit from where you saw that band was from a slightly older Bayesian calibration. And see, I'm over time, so I'm just going to flash my summary and just say that all the simulations that you saw were carried out on a calibrated fluid profile, which has been calibrated by fitting with data. All of them reproduce the PP once you get rid of the medium. The simulator just automatically goes back to PP. They have consistent recoil and a Q hat incorporation, and the Q hat and the energy loss is a multi-stage process. Okay, there's a high virtuality stage, a lower virtuality stage. It describes jets and leading hadrons. It describes the centrality dependence, the collision energy dependence, intrajet observables. There are minor issues with jet shape and with jet V2 and V3 that we are studying. But now the Bayesian analysis will give us a good idea of how close or how far we are from this picture of an HTL plasma. And with that, thank you for your attention.
Thanks, Abhijit.
And thanks, sorry for going over.
No, this is perfect. We started a few minutes later, so this is perfect. Questions, please? Okay, I have a few questions. Just see if there are other people.
Yeah.
Okay. Yeah. Go ahead. Sorry.
Yeah. Right. So I just wanted to check that I got your philosophy for doing this correct. So you're saying that in order to understand the full event, you of course need to follow everything,
Yes.
right? And that's what your Monte Carlos do. It's following the hard particles and it's following everything that it exchanges momentum with. Okay.
Yes.
And it treats the rest of the background as some hydrodynamic, in some
Yes.
hydrodynamic.
So the hydrodynamics is first run compared with data, right? And then you run the jets through it, but then every interaction with the jet,
You're
right, is then retained.
Yeah.
Yes.
And of course, if we could do this from first principles, then you wouldn't need extra variables. Okay.
Yes. Yes.
But you do, since we can't work out everything from QCD, therefore you need to have intermediate variables that track where you kind of switch off one kind of physics and switch on some other kind of physics and so on and so forth. And that's the stuff that you are kind of tuning through a Bayesian analysis of the data.
Yes. Thank you. That's right. That's another way of saying it. That's correct.
Okay, fine. Great. Thanks.
So that you
I'll
can
get
then
back to
focus
more-
on the things that you can calculate from first principles theory, and then you can sort of separate out the stuff that you don't, that we're just modeling parameters.
Yeah, I have more detailed questions, but I'll wait until other people get going and come back to it.
Other questions? Okay, so I'll ask one question if nobody else has any pressing one. So did I get this right, that the main reason that this 2014 result, which was showing different scalings at RIC versus LSC, got combined into a single blue band, was because your Q hat is now not just alpha S of MD, but it's a product of alpha S MD times alpha S of E times T, and E times T is higher at LSC and lower at RIG, and that's the main reason why this is coming. Is this a correct intuition, or there are other details that also matter quite a bit?
That is part of the story. So let me see, where was that? Right. So there is that. The energy changes. There's an energy also in the alpha S. So one of the alpha S is actually getting a lot smaller. Okay.
Yes.
And it's, if you stare at this for a while, you notice that alpha S is 1 over log of energy. So actually these logs cancel. So naively, actually, you think that, well, it's going to go down with energy, but it doesn't. Actually, after a while, it just doesn't change with energy a lot. So then, but it can still change with virtuality, right? And that's sort of what I was trying to get at. This was this, we've had this, I don't know why my keyboard doesn't work. We have it based on this selection model, but it's almost exactly the same argument as the people who say coherence, right? Which they're saying is that if the thing is very, very small, then the medium cannot really interact with it effectively, and that kind of reduces the Q hat. So Q hat depends on the virtuality as well, the effective Q hat. Okay, it could get much smaller, and you could say virtuality increases when energy increases, right? So that's all that is, you could think of it as an energy dependence as well. Right. So if you have all of these scale effects, then, and you keep track, as Arandu was saying, you keep track of all of the interactions with the jet, then you can explain a large amount of data. Okay, without the need for any reshifting between RIC and LHC. Yeah, that came out already. The moment you have this is the part that I sort of skipped over. Even in our first Bayesian analysis, where we didn't have that much detail in there, but we allowed for more dependencies inside Q hat. And you had a multi-stage formalism. There was a high virtuality and low virtuality stage. You already saw that you didn't need to reshift between RIC and LHC. Okay, so that's why the blue band came in, right? As opposed to having two separate normalizations. This band covered the whole region between RIC and LHC. But then that Bayesian, we compared a very limited amount of data. And when you do that, the error becomes much bigger. And that's why the band is so wide. So hopefully in quark matter, you'll see a narrower band.
Okay, yeah, great. And the second thing that I wanted to ask was, you said that if you have just you had an estimate of the tau during which the pure DClap evolution works roughly, and then later on the BDMPS is a good formalism to use. And then you said that actually if you include collisions during the DClap, then the DClap time also increases. But then that's not DClap anymore, right? It's some DClap plus collision. So it's some regime which is like intermediate between DClap and BDMPS or something like that? Or how does the formalism differ from DClap?
Right. So some of this is semantics.
Okay.
To be perfectly honest, how you transition from a region where you have mostly radiation and few scatterings to a regime where you have mostly scattering and few radiation, that is still an unknown. Okay, there's no calculation yet in that intermediate range. So we just, we have a scale that we say, it's like when you don't know exactly how to transition, you use this matching scale, right? You say above this, the theory is like this, and below this scale, the theory is like this, and let's have it match at this scale, and then we move the matching scale and see how sensitive it is to that. But back to your question, the scattering does change. It's not pure DClap anymore. Okay, but the scattering does not affect the fact that the virtuality of one emission is much larger than the virtuality of the next emission is much larger than the virtuality of the next emission. It's still falling. The scattering is only slowing down the rate at which it's falling, but it's not stopping the falling of the virtuality. So in that sense, it is DClap-like. It's medium induced, it's medium affected, but it still hasn't stopped the basic feature of this region that the parton as it's going along is steadily losing its virtuality, which is very different from the BDMPS phase, where the parton, if the medium was static, if the medium had no, if the medium wasn't dying, if the medium was static, then the parton would not lose virtuality. It would gain and lose and gain and lose and gain and lose. It would, every time it emit, it would lose virtuality, but then it would scatter, and then gain that back up again.
Yeah.
So in that sense, these are different phases. Okay, and so that's what I meant by the sort of the DClap phase, right? Which is the place where you are steadily losing virtuality.
Okay, thanks. Other questions?